Hello and welcome. In this video I will introduce you to the field of complex analysis, which is the study of functions involving complex numbers, often represented by the letter C. And by the end of this playlist, which I hopefully will be able to finish in about 20 to 30 videos, you will know everything you need to know to be able to easily pass a standard university course about the subject. To start off, we have to discuss why we even created this new set of numbers, the complex numbers, to begin with. The short answer is that our previous number system could not get the job done. Hence, we needed to add new tools to the toolbox. We needed to add new numbers. And this is something we have done many times before. Just look at how our concept of numbers have evolved over time. In the beginning, we only had our natural numbers, 0, 1, 2, and so on, which we could use to solve problems like this one here. But eventually, we stumbled upon a problem that we could not solve, like this one here, x plus 1 is equal to 0. This is simply a problem that we cannot solve with the current set of numbers that we have. We have to expand the toolbox, which we did by creating the negative numbers. And by combining our old numbers with our new numbers, we created a new set of numbers called the integers. And just like that, we now were able to solve these kinds of problems that we previously thought was impossible. We just had to invent some new numbers to do it. And everything worked great until it didn't. We once again stumbled upon a problem that we couldn't solve, like this one here, 2x plus 1 is equal to 0. So we once again had to expand our toolbox, which we did by creating the rational numbers. And a good thing to remember here when I say that we expand our toolbox is that we don't remove any old numbers, we just add new ones. Hence, the natural numbers are contained inside the integers, which in that turn is contained inside the rational numbers. So everything just piles on, we expand our number line. We don't remove any numbers. And by using this new set of numbers, the rational numbers, we could once again solve the problems that we couldn't before. The next roadblock that we stumbled upon is actually pretty famous. The problem was that if you wanted to find the length x in this triangle here, by using the Pythagorean theorem, you get that x raised to the power 2 is equal to 2. And the solution to this equation is not contained inside the rational numbers. So we once again had to invent some new numbers to be able to solve it. And that is why we created the irrational numbers. And by taking our old numbers, the rational numbers, and then adding the new ones, the irrational numbers, like the square root of 2 and the number e, for example, we get a new set of numbers called the real numbers. And by using these numbers, we were able to solve the problems that we couldn't before. The next problem arose when we were trying to find all the solutions to some polynomials. For example, if you have a cubic polynomial, then you are used to finding the solutions by plotting the graph and watching where it crosses the x-axis, which it should do in 3 places, one for each solution. But what if you have a polynomial that doesn't cross the x-axis at all? Take this for example, x raised to the power of 2 plus 2 is equal to 0. This one doesn't cross the x-axis at all, so we are not able to find the solutions by using our real numbers. And this is exactly why we once again expanded our toolbox by creating the complex numbers in this case, which we did by stating that I, which is also called the imaginary unit, is equal to the square root of minus 1. And until now we have been able to express our numbers by using one number line. But in the case of complex numbers, we actually need 2 number lines. One that we are used to, the real numbers, but then we also take that one and add a second one on top of it that goes perpendicular to the first one. And it is on this second one that we add this imaginary unit that we just created. So all complex numbers are made up of this imaginary part that goes along the y-axis and then a real part that goes along the x-axis. So if we now try to use this new set of numbers to solve our problem, we can see that we get that x is equal to plus minus the square root of minus 2. This can be rewritten as the following. And now we can use our new trick that we just invented, that I is equal to the square root of minus 1. Hence, the solution to this equation is that x is equal to plus minus the square root of 2 times I. And these two solutions are numbers that we can find in our two-dimensional plane here to the left. We can find one of them here and the other one here. And a good thing to remember here is that all of these numbers that we just have introduced to you, they are just as real or imaginary as each other. We invented them all, so the real numbers, for example, are just as real or imaginary as the next one. But one thing they all have in common is that we have been using them for centuries to be able to solve real-world problems. So in the next section here, I'm going to show you some examples about what each jump from one number system to the next one unlocked for us in our ability to describe our world. When we went from our natural numbers to the integers, we unlocked the ability to describe directions. For example, we could start talking about debt. I have 2 apples, but I owe my friend 1 apple. And this is now something that we were able to describe by using our mathematical symbols and numbers. And in the next step, when we invented the rational numbers, we unlocked the ability to talk about parts of something. For example, I have 1 apple and want to share it equally with 2 friends. I can now express that as the following. When we invented the real numbers, we unlocked the ability to more accurate measure our environment. So all of these objects that we only could approximate previously, we could now define precisely. And in the last step, when we managed to invent the complex numbers, we unlocked a whole number of things. 2 of the more important things, in my opinion, is that we got the solutions to all the polynomial equations that we talked about before. But we also got the ability to describe oscillations. For example, a pendulum swinging from a string attached to the ceiling, or the light waves coming from the sun, or the sound waves coming from my mouth right now. Anything more or less that can be described as a wave. And these are all systems that repeat itself. And you will see later on in this course that complex numbers are surprisingly great at handling these sorts of systems. So by now I hope I've been able to give you some background and context to why we even created the complex numbers to begin with, and the motivation behind it. So without further ado, let's continue by defining a complex number. A complex number, which we usually denote by the letter C, is a number that is written on the form C is equal to A plus B times I, where A and B are real numbers and I is the imaginary unit we introduced before, which is equal to the square root of minus 1. And as you can see here, a complex number is actually made up of 2 parts. You have A, which is called the real part, and you have B, which is called the imaginary part. So to visualize a complex number, we need 2 dimensions. We need one line that represents the real part of a complex number, and then we need another line that goes perpendicular to this one that can represent the imaginary part of the same complex number. So in this case here, for our complex number C, we have that the real part is A and the imaginary part is B. So to represent this complex number, we can mark it on a graph like this. The next thing we are going to do is to define the absolute value and the conjugate of a complex number. So we say that for a complex number C, which is equal to A plus B times I, we have that the absolute value of C, denoted like this, is going to be equal to the length of this complex number C. So that is simply the distance from the origin to this point in the graph here to the right. And this line, as you can see here, creates a triangle. And you can get the length of this complex number C, this line here, by using the Pythagorean theorem. And by using that one, we get that the length of a complex number is defined as the square root of A raised to the power of 2 plus b raised to the power of 2. We denote the conjugate of a complex number by the following, and this is simply the reflection of our complex number c in the real axis. So if we now go back to our figure up here to the right again, and take that complex number as an example, if we want to find the complex conjugate to this complex number, then we just have to reflect it in the x-axis. So we should be able to find this complex conjugate down here instead. And this is actually the same thing as flipping the sign of the imaginary part of a complex number. And if I haven't mentioned it before, this plane to the right here that we use to denote all of these complex numbers, that one is called the complex plane. There are actually many ways to represent the complex number. The one we just did when the complex number is written on this form here, that is called the standard form. But there are more ways to represent a complex number. For example, if we know the length of a complex number and the angle for it, then we can represent it in the complex plane as the following. And by now using our rules for sine and cosine, we can rewrite the expression for a and b as the following. And then we can insert these new expressions for a and b into our old standard form for the complex number. And if we do that, we get the following expression. We continue by simplifying a bit and we take out the absolute value of c. And if we do that, we get the following expression. And this new way of writing a complex number, that is called that we have written the complex number on its polar form. And the only two things we need to know to be able to write it out on this form here is to know the length of a complex number and its angle. Sometimes people also like to rewrite this expression here by using Euler's formula, which states that everything inside of this parentheses here are going to be equal to e raised to the power of I times alpha. And if we use this formula, we get that the polar form of a complex number also can be equal to the following. And something that you will notice later when you start doing some problems is that different forms are strong in different areas. Standard form is great for doing addition and subtraction, while polar form is more useful if you are doing multiplication or division, for example. Up next we are going to talk about how we do some basic operations like addition, subtraction and so on complex numbers. And you will probably recognize that the idea for all of these operations is the same as in real analysis. The only difference is that here we also have to take into account the imaginary unit, which work as a second dimension to each number. So we have two complex numbers up here, C1 which is equal to A1 plus B1i, and C2 equal to A2 plus B2i. And if we now want to do addition with these two numbers, then you simply add the real parts together and the imaginary parts together. And subtraction is pretty much the same thing, so we can take the thing we wrote up here and then move it down a bit, and then the only thing we do is that we change the signs in the parentheses. So we get that it is equal to A1 minus A2 plus B1 minus B2 times I. When we do multiplication, we do it more or less like in real analysis. We take the product of the two numbers by multiplying each term with each other. And if we write that out, we get the following. And now we can use the definition of the imaginary unit that tells us that I is equal to the square root of minus 1, and therefore I raised to the power of 2 is going to be equal to minus 1. So if we use that here and then rewrite this expression by gathering up all the real parts and then gathering up all the imaginary parts, we get that multiplication is defined as the following. The last thing is division. Let's say we have C1 divided by C2. So that is going to give us A1 plus B1 times I divided by A2 plus B2 times I. But we're not done here. What we want to do is to avoid having a complex number in the denominator. And we can fix that by multiplying with the complex conjugate of C2 on the top and bottom here. And if we do that and write out the expression, we get the following. And now you can see why we did this. Here you can see that in the denominator, all the imaginary terms take out each other. So the only thing we're going to end up with in the denominator is a real number. So if we just clean it up a bit and simplify it, we get the following expression for division. But hey, I told you that these last two operations, multiplication and division, was easier to do if you had the complex number on polar form, right? So let me show you why this is the case. Let's take these two complex numbers, for example, written on polar form, right? And if we now do multiplication as before, and we multiply each term with each other, and then we gather up all the real parts to the left here, and the imaginary part to the right. If we do that, we get the following expression. And now you might be able to see that we can use some identities for cosine and sine. More specifically, the one where you want to add two angles. And in our case, our two angles are alpha 1 and alpha 2. So if we use that identity for cosine and sine, we get the following. And in the case with division, we do exactly the same thing as we did before. We write out the expression, and then we multiply it with the complex conjugate of the denominator on the top and bottom here. And we do this once again to get a real number in the denominator. And I'm not going to bother you with all of the details here because that is not the main point of this lesson. But if we have done all of the calculations and simplified it a bit, we would have gotten that division by two complex numbers in polar form is equal to the length of a complex number C1 divided by the length of a complex number C2 times cosine of alpha 1 minus alpha 2 plus sine of alpha 1 minus alpha 2 times I. So in short, if you have two complex numbers, C1 and C2, and you multiply them together, then the new angle for this new complex number is going to be the sum of the old angles, alpha 1 plus alpha 2. And the length of this new complex number is going to be the product of the old lengths, the length of C1 times the length of C2. And in the case with division instead, we get that the new angle for this new complex number is going to be equal to A1 minus A2. And the new length is going to be equal to the length of C1 divided by the length of C2. So here you can see why polar form is a great way to do multiplication and division. The only really thing you need to know to use it is the length and the angle for your complex numbers. This is, however, not always so easy to acquire, but if you can get them, then polar form will be your greatest friend. So that was all the theory for this time. Let's continue by doing some examples. Can you help me decide which of the numbers here below that are complex numbers? And remember that a complex number is a number that can be written on this form here. The answer is that all of them are complex numbers. It is not as many might think that you need to have this imaginary part, an I, somewhere in your number. B can simply be equal to 0. And the other way around is also true. You don't need to have a real part to have a complex number. A can be equal to 0. And of course you can have all the different permutations with A and B here. So you can have that both of them exist, the real part and imaginary part, or that none of them exist. Another way to come to the same conclusion is to remember the things we talked about in the theory section. About how we expanded our toolbox. We added more numbers to the previous number systems, right? So this means that all the numbers we had before are contained inside of the complex numbers. And another great thing is that since all the other numbers are contained inside of this new number system, the complex number system, this also means that everything that you learn in complex analysis can be applied and used in all the previous number systems. So I'm pretty sure that somewhere in this playlist and in this course you will find a method or an idea or a theorem that you have been introduced to in a previous course, but you did not really know that it came from complex analysis in fact. In our next example, I would like you to write the following complex number on standard form and on polar form. And I would also like you to determine the absolute value for the complex number and also its complex conjugate. And the complex number in question is going to be C is equal to 2 plus 2i. So if we use the formula for the absolute value, we get that it is going to be equal to the square root of 2 raised to the power of 2 plus 2 raised to the power of 2, which is going to be equal to the square root of 8. For the complex conjugate, we swap the sign for the imaginary part, so we go from 2 plus 2i to instead 2 minus 2i. The complex number is already written on standard form here, so we only need to transform it to polar form. And to do that we need two things. We need the length, the absolute value of a complex number, which we have here. And we also need its angle, which we can determine from the figure to the left here. And in the figure we can see that the complex number splits the first quadrant evenly. So we go the same distance on the x-axis as on the y-axis. And therefore the angle for this complex number is going to be 45 degrees. Or as I like to say, pi divided by 4. Which is exactly the same thing, just expressed in the superior unit. And now we can use one of the two formulas here to the right to express this complex number on polar form. And just remember that both of these two are correct. Both of them are a valid way to express a complex number on polar form. So just pick the one you like. If we use the first one that uses Euler's formula, we get the following expression. Meanwhile, if we use the second one that uses cosine and sine instead, we get the following. In our next example, I would like us to do the calculations and then make us visualize the effect, so you really get the hang of what these operations do to the complex number in the plane. So 2 times I is equal to 2i, and then we have that 2i times I is equal to 2 times I raised to the power of 2. And here we know that I raised to the power of 2 is equal to minus 1, so this thing becomes minus 2. On the next row we have 2 times I raised to the power of 2 times I. And we already know from the last example that the first part here is equal to minus 2. So this becomes minus 2 times I, which simply is minus 2i. On the next row we have 2 times I raised to the power of 3 times I. And this is equal to 2i raised to the power of 4. And if we split this thing up, I think the next step is going to be more clear, that we have 2 times I raised to the power of 2 times I raised to the power of 2. And if you remember, I raised to the power of 2 is simply going to be equal to minus 1. So this thing is 2 times minus 1 times minus 1. So this is going to be equal to 2. On the last one we have 2 times I raised to the power of 4 times I. And here we know from our previous example that 2 times I raised to the power of 4 is equal to 2. So this one simply becomes 2 times I, also known as 2i. And now you might be able to see that the pattern repeats itself. We started with the number 2, and then we multiplied it with I 1, 2, 3, 4 and 5 times. And as you can see, we got back to the same number that we started with, the number 2, after 4 iterations. And this is no coincidence, which you are going to see for yourself when we now continue by visualizing this operation in the complex plane. So we started with the number 2 over here, and then we multiplied it with I, which took us to 2i. And if we multiplied with I again, then it took us from 2i to minus 2. If we did it one more time, we ended up at minus 2i. And if we did multiplication with I one more time, we ended up where we started, at the number 2. So here you can see that multiplication with I is the same thing as rotating the complex number by 90 degrees. And this is also the reason why you get back to the same number after 4 operations. Since after 4 operations we have made one complete cycle. And then the pattern just repeats itself. We can't reach any other numbers than these 4 here. And this way to think about multiplication, to think about how it changed the geometry of a number in question, it is really useful in complex analysis, but you have probably already used it in real analysis before. Take for example, if you multiply a number by minus 1. If we start at the number 2 again, Then we go from 2 to minus 2, and then back to 2. So multiplication with minus 1 is the same thing as rotating the number by 180 degrees. And we only need to do it 2 times to make one complete cycle. In our next example, I would like us to do the calculations and then once again visualize the effect. And here we're going to start with some addition. So we have two complex numbers, let's call them C1 and C2, and we want to add them together. The way we do this is that we do it in 2 steps. We add the real parts and then we add the imaginary parts. In this case, we get that the real parts are 2 plus 4, right? And the imaginary parts are 3i plus 2i. And if we simplify this, we get that this thing is equal to 6 plus 5i. And if we now try to visualize this operation in the complex plane, then you can see that this is the same thing as taking the complex number C2 and placing it on top of the first complex number C1. And then you just check where you end up if you travel along C1 and then continue along C2. Because that point at the end of this trail, that is going to be equal to the complex number we are after. So in this case, as you can see, 6 plus 5i. In our next example, I would like us to try some subtraction. So if we do that with these two numbers here, we get that the real parts are going to be 2 minus 3, and then we add the imaginary parts, which is going to be 2i minus 1. And if we simplify this expression, we get that this is going to be equal to minus 1 plus I. And for our visual representation, we can actually think about this operation in 2 different ways, so make sure to pick the one you like the most. The first way is that we don't think about this as subtraction, we think about it once again as addition. We have one complex number, C1, and then we want to add a second complex number, but in this case minus C2. And as we discussed before, to multiply something with minus 1 is the same thing as rotating the complex number by 180 degrees. And if we do that and then place the result of this operation at the end of a complex number C1, then we can once again just follow the trail to get to the complex number that we want. In this case, minus 1 plus I. The second way to think about subtraction is that it describes the distance between two complex numbers. In this case, the distance from C2 to C1. Notice here that we actually have an orientation. We are going from C2 to C1. And then you simply take this new arrow and place it at the origin. And it will simply point you to your new complex number that you want. In this case, minus 1 plus I. In our next example, we are going to do some multiplication. So we start as you are probably used to, that we multiply each term with each other. And if we do this, we get the following expression. And here we can see that we have I raised to the power of 2. And that is equal to minus 1. So this thing becomes minus 2. So if we use that and then simplify a bit by gathering up all the real parts as 1 and then all the imaginary parts as 1, we get the following. And there is not really so much more that we can do here. One thing we might be able to do is to see that we have some common factors that we can take out of a parenthesis. For the real part, that's going to be minus 2, and for the imaginary part, that's going to be 2i. But I told you before that these kinds of calculations are easier to do if you have your two complex numbers on polar form. So we are going to continue by rewriting our two complex numbers up here on polar form and then do the calculations again. And to do this, we need 2 things. We need the length and we need the angle for each complex number. And this is easier done if we try to visualize them in the complex plane. To determine the angle for C2, we can see that it goes the square root of 3 steps in the x direction, while it only goes 1 step in the y direction. So if we look at the table for the standard angles for our trig functions, we can see that the angle for C2 is equal to pi divided by 6, since this row corresponds to the ratios that we also have. And the length of this complex number is, as we learned before, equal to the square root of a real part raised to the power of 2 plus the imaginary part raised to the power of 2, which in this case is going to be the following. And if we simplify this, we get the square root of 4, which is equal to 2. And in the case with our next complex number C1, we have that this one divides the second quadrant equally. So the angle in this case is going to be equal to pi divided by 2, since we are passing through the whole first quadrant. And then we need to add half of a second quadrant. So in that case, pi divided by 4. If we work this out, we get that the angle is going to be equal to 3 pi divided by 4. The length can be determined the same way as before. But in this case we have that minus 2 is going to be the real part and 2 is the imaginary part. And if we work this out, we get that the length of a complex number C1 is equal to the square root of 8. And now we have everything we need. So we can rewrite the two complex numbers up here that are written on standard form to polar form by doing the following. And now we can once again try to do the multiplication. But here I want you to remember the neat trick that if you multiply two complex numbers on polar form, then in short the only really thing that you do is that you multiply the lengths and then you add the angles together. And if we do that in this case, we get that the new length is going to be equal to the square root of 8 times 2, and the new angle is going to be equal to 3 pi divided by 4 plus pi divided by 6. And we can try to simplify this angle by creating a common denominator. So we multiply the left division by 6 at the top and bottom, and then on the right division we multiply by 4 on the top and bottom. And if we do the calculations, this becomes equal to 18 pi divided by 24 plus 4 pi divided by 24, which is equal to 22 pi divided by 24, which can be simplified to 11 pi divided by 12. And by inserting this back into the expression up here, we get the following. And now if you want to visualize the operation, we say that if we have two complex numbers, C1 and C2, and we do multiplication with them, then it is as we said before, the angle for this new complex number is equal to the sum of the two previous angles, and the length of the complex number is equal to the products of the old lengths. But let's say we want to do division instead, but with the same two complex numbers. Then the trick here is that we instead are going to divide the length and subtract the angle. So in this case we get the following. The length is going to be equal to the square root of 8 divided by the length of a second complex number, so in this case 2, and then the angle is going to be the first angle, so 3 pi divided by 4, and then subtract the second one, so in this case pi divided by 6. And now we can once again try to simplify this angle by creating a common denominator, which we do the same way as before. On the left division, we multiply by 6 at the top and bottom, and on the right division, we multiply by 4. And if we do that, we get 18 pi divided by 24 minus 4 pi divided by 24. And if we do the calculations, we get that this is equal to 14 pi divided by 24, or 7 pi divided by 12. And if we insert this up here, we get our final answer. And we can of course try to visualize this in the complex plane again. So if we have two complex numbers, C1 and C2, and want to do division, so C1 divided by C2, then the new complex number that we create by doing this operation will have that its angle is equal to alpha 1 minus alpha 2, and then the length of this new complex number is going to be equal to the length of C1 divided by the length of C2. So that was all for this time. We covered a lot of material, so good job at getting to the end here. And I hope that you learned something new about complex numbers. And I think that this video is a good representation of how I structure all of my videos in this playlist. We always cover all the necessary theory about the subject, which we illustrate by doing some examples. And I always try to make my explanations go step by step so you can really follow along, and not that you have to guess about anything that I do. And at the same time I try to be as concise as possible, because I want to respect your time. I will only include the part that you need to know to understand the subject, and my explanations will be quick and to the point. And you can always write to me in the comments if you have any questions about the things that we cover in the video lessons, and I will try to help you to the best of my ability. So until next time, thanks for watching.